All right, hey everyone. This is going to be a quick tutorial on different types of enzyme inhibition. And we're mostly going to be looking at kinetic graphs in this set of examples here and understanding how different types of inhibitors are going to affect those relationships. So real quickly, I want to start by looking at a couple of our classic kinetic graphs, and then from there, we'll look at some examples. So I'll break this video down into chapters in case you want to skip around, but we'll be covering the four different types of inhibition that are most commonly sort of been in introductory biochemistry as the different types of inhibitors we might encounter in a simple system. So the first thing I want to look at are the two types of classic kinetic graphs that we often look at when we're trying to quantify enzyme function. And the first thing I want to be able to do is identify some key features on these graphs, because these are the things that are going to dictate how the graphs will change when we take a look at different types of inhibitors. So for our Michaelis-Menten relationship, we'll just recall that this is a graph where we're plotting a initial rate of catalysis against a function of increasing substrate concentration. So a few things that we can point out on here. Eventually, if we add enough substrate to our mixture here, right, the relationship that we're looking at when we're modeling these things in a simple Michaelis-Menten type model here is that we have substrate binding occurring first, and then there's a complex that forms, and then there's a catalytic step where the enzyme converts the substrate into products, and then there's a rapid release of products here. So the simplest model that we can think of is sort of documented down here. And eventually, when we have enough of the substrate present at the very start of our reaction that we're trying to get started with our enzyme catalyzing it, eventually, if we have enough substrate, we're going to saturate all of the binding sites on that enzyme, and that's going to bring us closer and closer to ultimately this maximum initial velocity that our enzyme can have up here. So the asymptote that this graph is going to approach is our Vmax. And the other thing that we can point out on this graph is that when we're halfway there, right, the Michaelis-Menten relationship tells us that at half Vmax, we can read across the graph kind of like we do with a binding curve when we're looking at proteins and ligands, which is another relationship that we often cover, right? There's a particular concentration where we reach half maximum velocity, and that concentration is going to be equal to the Michaelis constant, or Km, down here. All right, so there's a couple things we can read on that graph. These constants, the Vmax and the Km, are going to be unique to a particular enzyme under a certain set of conditions. And it is a little bit hard to pull those parameters off of a straight Michaelis-Menten graph without doing some nonlinear curve fitting. And it's a little bit easier if we can linearize the data. As these days, we often are able to just pull the parameters straight off of a Michaelis-Menten plot, but it can still be helpful to look at the linearized form where which is our Lineweaver-Burke relationship, right? This is where we've taken a double reciprocal plot where we take both variables and just invert them and then plot them. And it turns out that this relationship will give us a linear plot, which will be much easier to fit. And there's a couple of things to point out here as well. So once we've done that, our y-intercept is one of the important points that we're going to call attention to. And this is where we're going to find our Vmax value. And actually, the value of the y-intercept here is 1 over Vmax, right? And then our x-intercept also gives us really conveniently some information about the other constant that we're interested in. And this has a value of -1 over Km, okay? So we have 4 types of inhibitors, and the first one I'm going to talk about is competitive inhibition, talking about competitive inhibitors now. And competitive inhibitors have a really unique property, which is that they sort of look like the substrate. So we can kind of see that in these sort of cartoon plots here. We have a substrate that sort of has this hexagonal shape, and then an inhibitor, which at least partially looks like it has the same structure as that substrate. And as a result of this, we can have both of these molecules bound to the same binding site on an enzyme. But the main thing that separates competitive inhibitors from other types of inhibitors we'll see is that the enzyme active site only has room for one of these molecules at a time, right? And so you can basically have a branching path here where either the enzyme is going to bind the inhibitor or it's going to bind its regular substrate when both of these things are present in our solution, right? So thinking about how this affects the graph, the first thing to point out here is that when we actually look at this place in this mechanism where we're branching here, we're not really affecting anything related to the catalytic step here, right? So the actual rate of catalysis isn't affected by competitive inhibitors. Instead, all they're doing is sort of taking up space in the active site and creating this branched path where sometimes the active site on the enzyme is blocked, so the normal substrate can't bind there, right? So we'll note those points down, and then we can talk about how this is going to affect the graph. Okay, so thinking about the relationship here, we are looking at how this is going to affect the graph. And one of the things to point out is that the main two things we need to decide on are what the effect on Vmax and Km are here. So let's consider Vmax first. So if we look at this mechanism, the enzyme substrate complex is forming on one path and the enzyme inhibitor complex is forming on another path here. So sometimes once we're in this inhibited state, right, the enzyme can't bind its substrate anymore. And so sometimes the active site is going to be blocked. But we could imagine that if we really crank up the substrate concentration, if we go high enough with the amount of substrate that we've added to our mixture, eventually there's going to be more and more and more of this substrate present, which makes it more and more likely for this enzyme substrate complex to bind relative to the enzyme inhibitor interaction that's happening here. So basically, if you have enough substrate present, you can outcompete the competitive inhibitor. And if that happens, if the amount of inhibitor essentially becomes negligible, then this process is going to happen with no change, and you're essentially going to get back to the same level of function that you had before. So what that means for us is that actually the maximum possible velocity that you can get to here is not going to change. Because if you add enough substrate, you're going to be able to outcompete your inhibitor and eventually we'll reach that same high functioning level that we're seeing in the original graph. But because the enzyme substrate complex can't form when the inhibitor is bound, that is going to change what is apparently happening with our Km here, right? The enzyme still has technically the same affinity for the substrate, but because oftentimes this, at least at high inhibitor concentrations, this active site is going to be blocked. What that ends up meaning is that it's going to look like the enzyme is worse at binding the substrate than it actually is when there's an inhibitor present here that falls under this competitive label. And if the enzyme is looking like, at least, that it's worse at binding its substrate, then what we have here is an increase in the apparent Km value of our enzyme. So with the presence of a competitive inhibitor, we increase Km and we have no change on our Vmax. So Vmax for our inhibitor, I'll put this in red on the slide here, is going to be exactly the same. We can basically draw those lines overlaid with each other, right? So our Vmax, our inhibitor, is still the same. Our Km is going to be a little bit different though, and I can highlight half Vmax on my slide here. So that means that our original value for Km is here. If Km increases, we're going to have to move that out a little bit on the graph to a new point. And that's the point that our graph will now have to intersect. So our inhibited form is going to have a curve that's a little bit more stretched out, right? We still have that hyperbolic shape and we're still approaching this same Vmax up here, but we're going to take more time to get there because the graph needs to be sort of horizontally stretched to pass through that second Km value. All right, next I want to look at what happens with our Lineweaver-Burke plot. And because we've sort of talked through this, I'm just going to pay attention to my features that I've highlighted over here. So we have Vmax not changing and Km is going to increase. All right, so let's think about how that affects our graph. First of all, if Vmax doesn't change, that means that our 1 over Vmax on the graph here is going to stay the same, right? So our inhibited state is still going to pass through that point on the Lineweaver-Burke plot. If the Km increases, this is the one that's a little trickier. We have to think about what that'll do to the x-intercept, right? We know the x-intercept here is equal to a value of 1 over, or negative 1 over Km, right? So if Km gets bigger, right, that means that the denominator of that fraction is going to get larger, and that means that the number here is going to decrease in magnitude, right? If we just take a look at this value and we increase the denominator, then this value is going to get smaller and smaller, less and less negative, and it's going to approach 0, right? So we're going to be shifting this x-intercept here over to the right on this graph. And this would be our x-intercept for the inhibited state, right? And now all we have to do, now that we have 2 points, is draw a line connecting them. And there we are. So what we can see here is that when we have a competitive inhibitor, it sort of looks like we're pivoting when we rotate this line from our original plot here up to the inhibited state. We're getting a steeper slope, and we're pivoting around this Vmax y-intercept point there. All right, the next type of inhibition I want to take a look at is something called uncompetitive inhibition. And this one has a different type of mechanism to it. Taking a look at our mechanism and how that original mechanism is affected by having this inhibitor present, we have a different part of the diagram that's being interfered with, right? And with uncompetitive inhibitors, what we end up having is the enzyme can bind the substrate just like it normally would, and there's no interaction there. But then after the substrate is bound, this is where we branch. In one case, when there's no inhibitor around to interfere, we have a conversion of substrate to products just like we normally do. But if there's an uncompetitive inhibitor around, the inhibitor can bind to this complex and stop the catalysis from occurring. So we end up with this enzyme substrate inhibitor sort of 3-part complex here. And this complex can't proceed to products until that inhibitor ends up dissociating and allowing this reaction to finish, right? So visually, what this often looks like is you've got some substrate that's coming into an active site here, and that's sort of the normal picture we have. But then there's some regulatory site. Often this regulatory site is nearby or coupled in some way to the active site. And when the inhibitor comes in and binds, this interferes in such a way that this catalysis can't take place. So we can think of this as sort of binding and locking up the active site and keeping it from actually undergoing that chemical change. All right. So in terms of how this affects the graph, there's a couple of things to point out here. Actually, there's 2 effects that we're going to see. First of all, let's just put on the slide just the general points that we've outlined so far. All right, so let's think about how this could work and how this could affect our kinetic parameters here, Vmax and Km. Right, we'll try to chop through this logically. So in terms of effect on Vmax, this is a different situation to what we saw with the competitive inhibitors, because in that case, when we were looking at competitive inhibitors earlier, right, the only thing that's being affected is the ability of the enzyme to bind to the substrate. And so if you have enough substrate around, eventually you can outcompete the competitive inhibitor, and you can have the normal function that you'd expect to see at the extreme high concentration of a substrate, the extreme right side of the graph. That's not going to be the case with uncompetitive inhibition. It doesn't matter how much substrate you have, right? Once you've formed this enzyme substrate complex, as long as there's at least some inhibitor around, there's still a chance that that inhibitor is going to bind to your complex, no matter how much substrate you have in your mixture, and prevent the catalytic mechanism from occurring as intended, right? And so that actually is going to affect Vmax, right? No matter what, having some uncompetitive inhibitor in your mixture is going to stop some percentage of your enzymes from completing their catalytic mechanism even after they bind to their substrate. So hopefully it won't be too hard to imagine that this is going to decrease our Vmax. Okay. And on the graph, remember Vmax is represented by this asymptote that we're reaching on the Michaelis-Menten curve. So what we're going to end up doing when we decrease Vmax is lowering the ceiling. I'm going to do this in a pretty dramatic way here so that we can really see the difference between the curves. So this would be our inhibited Vmax, our Vmax asymptote in the presence of an inhibitor. That's actually not all that happens here. And we have to consider the effect on the apparent Km as well. And probably the simplest way to explain what's going on here is just to refer back to the old Le Chatelier's principle that we think about with equilibrium, all right? So thinking back to general chemistry, when we do something to upset the equilibrium in a process, we often will see the reaction adjust to reestablish equilibrium. And we can think of this binding of the substrate to the enzyme as a simple event that can be represented by equilibrium here. What the inhibitor is doing is removing some of that enzyme substrate complex from this equilibrium that I highlighted up here, right? And so if that happens, you're essentially removing a product from the reaction here, and that's going to cause our Le Chatelier's principle to shift equilibrium to the right, okay? And meanwhile, another thing about competitive or uncompetitive inhibitors is that while they're bound, the substrate can't leave the active site. So the substrate is sort of locked in there as long as the inhibitor is bound, and then it's only after the inhibitor is released from its binding site that we can go back to this enzyme only situation over on the far left there. So a couple ways to think about what's going on here. But ultimately, what's going to happen is the apparent affinity of this enzyme for its substrate is going to increase because we're going to end up with equilibrium shifted such that this enzyme substrate complex, whether it has inhibitor present or not, is going to start to dominate more than it did before, right? So Km here, if affinity increases, Km is also going to decrease. The apparent Km here is going to be smaller. All right. So what effect does that have on the curve? Well, if our original Km was at half Vmax here, we have to be careful. And I'm going to draw my original Vmax in black here so that we can sort of visualize carefully that this was our original half Vmax point. But now that we've lowered the ceiling, our half Vmax point that goes along with our lowered inhibitor Vmax is going to be a little bit lower on the graph, somewhere down here, right? So this is half Vmax of the inhibited complex. Okay, so along with this, we are going to highlight where our Km should be. And let's just do that for our original curve. Then we can figure out where to put our inhibited Km. Okay, if Km gets smaller, that means Km has to shift to the left. So we're going to end up, let's say, somewhere like that. That means that our graph is going to have to go through this point, right? So we've kind of changed two things here, and I have to draw a hyperbolic curve that passes through this point. So it tightens up a little bit to the y-axis there, but it also approaches a lower value for the maximum velocity as we start to saturate the binding sites. All right. So once again, I'd like to also look at what happens with our Lineweaver-Burke relationship. And now we have two things decreasing. So what is that going to do to our curve? Well, we said before that if Km increases, that moves our x-intercept closer to the origin of our graph, closer to 0. So if Km decreases, stands to reason that we're going to shift it left, right? And likewise, now we just have to look at what's going on with Vmax. This time, unlike the competitive inhibitor case, Vmax is going to change. And typically, the relationships that we're going to look at are going to have both of these things changing in a proportional way. So as Km decreases and shifts our x-intercept to the left, our 1 over Vmax value here is going to decrease as well. And that is going to make this value bigger overall, right? Because as the denominator gets smaller, the overall value is going to get larger. So we're going to go more in the positive direction here, all right? And these are often, we're going to see that these change in proportional ways, such that we end up with the same slope of the line as we did before, all right? And so the line that we would draw here is just parallel to the first one and going through this new set of points. Right, if I can get that to intersect properly there. Okay, so one way to recognize uncompetitive inhibition really easily on a Lineweaver-Burke plot is just to look for those parallel lines, because this is the only kind of inhibition that we're going to see where this occurs in this way. All right, finally, we have the messy one. This is mixed inhibition, and there's clearly a lot more going on in this situation, but basically, we just have fewer rules than we did before about when the inhibitor can be bound to the complex. So we have a whole bunch of different equilibria that we can look at here, and that's why this one tends to look like a little bit of a mess. Basically, the only restriction we've removed is that either the enzyme substrate complex or the enzyme by itself can be bound by inhibitor now. So that definitely makes the picture a little more complicated, but it also contains elements of both of those previous types of inhibition that we've seen. The important thing to note is that when the inhibitor is bound, we have no path to the products, right? The inhibitor has to come off before the products can actually form and before this catalytic step can be carried out here. So whether or not the enzyme is bound to a substrate or not, with either one of these cases down in the bottom part of my diagram, right? If that inhibitor is present, we can't proceed to products. So just like uncompetitive inhibition, this is going to interfere with the maximum speed that our enzyme can turn over products. Because no matter whether you have a ton of substrate or not very much at all, there's always a chance that an inhibitor can come in and bind and keep your enzyme from turning over products as long as it's bound, right? So that is going to affect our maximum velocity. In terms of what happens to Km, though, things are going to be kind of complicated here. Because what ends up happening with a mixed inhibitor is that when the inhibitor is bound, the substrate can still get in there, but generally speaking, it's not going to happen as easily when the inhibitor is sticking there. In our cartoon, hopefully this is sort of represented by the fact that our inhibitor is not binding right in the active site, but it's sort of binding nearby, making it a little harder for our substrate to get bound. So the equilibrium here is not going to be the same as the equilibrium that we're drawing for just the substrate alone binding to an empty enzyme active site. So mixed inhibitors affect substrate binding, but they also affect catalysis. And something about the Km is going to change. We can talk about the different scenarios there. Just to summarize what we've put on the slide so far, we're going to write down some points now, right? So to summarize, we can bind our inhibitor to the enzyme alone or to the enzyme substrate complex. We are going to prevent catalysis when the inhibitor is bound. And there's also an effect interfering with substrate binding in the first place. So a lot of stuff going on here. In terms of how this affects our kinetic parameters, we have Vmax again that we have to consider and Km. And hopefully based on our discussion with uncompetitive inhibitors, we can recognize that when the inhibitor is bound to the enzyme substrate complex, right, which is a scenario that is present in our diagram here, that's going to interfere with the rate of the reaction that can be carried out after that complex forms. So just like with uncompetitive inhibition, we're going to see a decrease in Vmax here, which is going to correspond to a lowered ceiling for our curve when we consider it on the Michaelis-Menten plot. Now, as I said here, the effect that Km is going to experience is going to be different depending on the situation, right? If we have a situation that's more like an uncompetitive inhibition case, where the equilibrium and the rate of inhibitor binding is greater when the substrate is already bound inside the complex here, right? Then we're going to have a situation that's very similar to what we were looking at with uncompetitive inhibition, right? That's sort of Le Chatelier's principle kind of mechanism where we have the substrate locked up in the active site, and then Le Chatelier's principle is going to kind of pull that reaction that we're representing by that substrate binding to the enzyme towards the rightward direction, and the enzyme substrate complex is going to be more favored in that equilibrium now that we have the presence of the inhibitor, right? And that would decrease Km, or at least the apparent Km that this enzyme has when the inhibitor is present, right? So that would lead to a decrease. But on the other hand, we could also have a situation where the ability of the inhibitor to interfere with substrate binding is sort of the more dominant characteristic of this inhibitor. So if this equilibrium is a whole lot worse for the enzyme substrate complex than this equilibrium is with our original enzyme here, and if this is the process that sort of dominates more in this setting, then we might have a situation that looks a little more like competitive inhibition, where it sort of looks like the enzyme is worse at binding its substrate than it would be if there were no inhibitor present, and that would increase Km. So all we can really say here for a generic mixed inhibitor is that there's going to be some sort of change to the Km value, right? But it's sort of which direction that goes in is going to be a balance between these two sort of competing elements of the mixed inhibitor diagram. All right. So for my example here, I'm just going to note real carefully that I'm going to use an example where we are increasing Km, but we could easily do the other one on this graph, right? So once again, I'm going to highlight my elements of my graph here. 1/2 Vmax for our original enzyme looks to be about there on our graph. But since we've lowered the ceiling for our inhibitor, we have to put another 1/2 Vmax for our inhibitor on our graph, and that's going to be in a different location. And likewise, we can read across the graph to where our original Km was on our x-axis here. And this time, what I'm saying is my example of a mixed inhibitor that I'm going to show you here is where Km is increasing. And so if our new Km is further out here, I have to get my graph to go through this intersection point that I'm highlighting on the graph now. So we're going to end up with a much more stretched out curve, but it also is going to reach a lower ceiling at the end of the day. And I don't have room on my graph to really show this, but eventually this graph is going to approximate and asymptotically approach that lower Vmax ceiling. So next, let's look at what this does to our Lineweaver-Burke plot. And we're just going to follow the same conventions that we already kind of talked about with some of the others. If Vmax decreases, this is going to be the same situation that we saw for our uncompetitive case before. And if 1/, Vmax is going to increase if the Vmax property itself decreases. So we're going to end up with a y-intercept that's higher up on our Lineweaver-Burke plot. For my example here, this is probably the more common case that we often see. Again, for this specific example I used, I am saying that Km is increasing here. And this was similar to what we saw with our competitive inhibitor case, where our x-intercept is going to shift to the right a little bit. And if I draw a line through those 2 points, I get my new curve for my Lineweaver-Burke plot here. And it looks like our intersection point or pivot point where these graphs are sort of adjusting is sitting somewhere in my second quadrant, right? Which is unique for mixed inhibition of this type. All right. Now, there is a form of mixed inhibition where we see a decrease in the apparent Km. And if I put this on the graph, we'll just be moving in the other direction when it comes to placing the second point on our x-intercept here, right? This is going to make the graph look a lot like our uncompetitive example, because that's exactly the relationship that was happening in that case, but it's not necessarily going to be a proportional change here. So I think my graph sort of illustrates this fairly well, right? Eventually, and we're almost there with the lines that I've drawn here, you're going to end up with a intersection point happening in the third quadrant of the graph, right? Most likely, these lines are not going to be parallel. So there's two possibilities here for mixed inhibition. The more common one is the one that I have outlined in red that we will generally see exhibited for us, where there's an apparent increase in Km, but it can go both ways. And it really comes down to which one of these paths is more favored for the inhibitor to bind, whether it's the enzyme alone or the enzyme substrate complex. If the enzyme alone is favored, then we're going to get something that looks a little more like the competitive inhibition situation, and we'll get the red line. If the enzyme substrate complex is the form of the enzyme that the inhibitor wants to bind to more, then we're going to end up with something that looks a little more like the green graph. All right, so now we've covered 3 out of the 4, and I'm actually going to stay on this slide for the last one, because the last type of inhibition that we're going to look at here is basically just a variation on mixed inhibition here. So the one that we're going to talk about in our final example, there's a reason why we're covering it last, is something called non-competitive inhibition. And this one is really just a variation, a special case that we can talk about for our mixed inhibition example here. So it's the same type of diagram that we looked at for mixed inhibition. All these same things that I outlined down below here are true. The main difference here is that with mixed inhibition, you have either an increase or a decrease in Km. And that's going to be controlled by whether or not, respectively, you have the enzyme alone that's being favored as a binding partner for this inhibitor, or whether the inhibitor would rather bind to the enzyme substrate complex. That would give you an apparent decrease in Km, right? So it could be either or, and to varying magnitudes, depending on how unbalanced we are between this inhibitor's preference for the enzyme alone or just the complex together. A non-competitive inhibitor is a case where this process, these two competing models for how the inhibitor can bind, those are perfectly balanced with each other. So rather than having an increase or a decrease in Km, you actually have a special situation where there is no change. Okay, everything else about the mixed inhibitor model is the same, but it's the balance between those two pathways that gives us a non-competitive case. And I'm just going to leave the Lineweaver-Burke plot up for this one and show you just the one example here. Hopefully, as an exercise for the viewer, you can take a look at the Michaelis-Menten graph at some point and figure that out. But once again, just like we did with our normal mixed situation, right? We have a apparent decrease or a decrease, a real decrease, I guess, in Vmax. And so that's going to put our y-intercept a little higher on our Lineweaver-Burke plot. And if Km doesn't change, we're just going to keep it the same in this case. So that's what ends up happening here. And if we draw a line through these 2 points, we can really easily recognize a non-competitive inhibitor, because the pivot point for where that graph is going to superimpose itself and intersect with other plots is when we reach that x-intercept. All right. So I hope this was a helpful summary of the different types of inhibition. We've looked at the effect that each of these has on the Lineweaver-Burke plot especially, and we also have looked at some examples of just regular Michaelis-Menten graphs and how those will change. But obviously the Lineweaver-Burke plot relationships are a little bit easier to see, and so those are often the things that we focus on when we're just talking about basic enzyme kinetics. All right, thanks for watching, and I'll catch you in the next one.